Good morning to all. Today we are going to see about the principle of light propagation through the fiber. The outcome of this section or this topic, after completion of this section, the students able to explain the principle of light propagation through the fiber. Usually, the serial bit stream in electrical form is presented to a modular which encodes the data appropriately for the fiber transmission. A light source is driven by the modular and the light focus in the fiber. The light travels down the fiber and at the receiver end the light is fed to the detector and converted to the electrical form. The principle of light propagation through the fiber is total internal reflection, acceptance angle, numerical aperture and skew mode. First, let us see about the total internal reflection. It can be consist of index of refraction and Snell law. First, let us see about the index of refraction. This is a measure of speed of light is in respective medium. It is calculated by dividing speed of light in vacuum to the speed of light in material. The Ri of vacuum is 1. For gliding material, the optical fiber is 1.46. The core value of Ri is 1.48. So, the delay in communication will be due to the communication equipment switching and decoding, the encoding and voice of fiber. Second one, Snell law. In order to understand the ray of propagation fiber, this is called Snell law. So, where n denotes from the diagram, the n denotes the refractive index of material theta. Critical, if we consider, we notice above the angle theta 1 becomes larger than the theta 2. Because of refraction effects, theta 2 becomes larger more quickly than the theta 1. At the same point, theta will reach the 90 degree, while theta 1 still will less than that. This is called critical angle. Next one is total internal reflection, TIR. When the light traveling in a dense medium hits a boundary at a steep angle, is nothing but larger angle, the light will be completely reflected. This phenomenon is called total internal reflection. This effect is used to optical fiber to confine the light in the core. The light travel along the fiber bouncing back and forth of the boundary. If we consider the above figure, we can see the effect of critical angle. Light they enter the fiber certain range of angle can travel down the fiber without leaking out. The total inner reflection occurs when the glass occurs from higher refractive index to lower refractive index material. So we see that the ray where the angle theta 1 is less than the critical value, the ray will be propagated along the fiber, will be bound within the fibers. In figure 1 we see that where the angle theta 1 is greater than the critical angle, the ray is refracted into gliding and will be ultimately lost outside the fiber. Next one is acceptance angle theta A. The maximum incidence angle below which the ray undergoes the total internal reflection is called acceptance angle. The cone is referred an acceptance cone. We consider rays entering the fiber from the outside. We see that there is a further complication. The refractive index difference between the fiber core and the air will be causes any driving ray to be refracted. This means that there is a maximum angle for a ray arriving the fiber end phase at which ray will propagated. The refractive angle less than the angle will propagate, but rays arriving the greater than the angle. Next one is numerical aperture NA. It is defined as a sine wave of acceptance angle of fiber. So NA is nothing but numerical aperture is equal to sine I max. One of the most often quoted characteristics of optical fiber is numerical aperture. The numerical aperture is the intended measure of light capturing ability of fibers. However, it is used of many other purposes. For example, it may be used as a measure of amount of loss we might expect on a bend of particular radius, etc. This one will reach one core gliding interface at an angle smaller than the critical angle. It will pass into the gliding. This will eventually be lost. It's clear that there is a cone acceptance. It may enters the fibers at the angle within a core, then it will capture and propagate at bounded mode. If the ray enters the fibers at an angle outside the cone, it will leave the core and eventually leave the fiber itself.